I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College. This is the third lecture of Module 12. I choose the topic in Module 12 is low temperature physics. This is the third lecture. That means in my previous lecture, lecture 1 and in lecture 2, I have discussed Joule-Thomson effect, Joule-Thomson porous plug experiment. I already discussed, and JT or Joule-Thomson effect versus reversible adiabatic expansion. Now, and the next lecture, that means in lecture 2, I have discussed enthalpy change in JT expansion or enthalpy change in Joule-Thomson expansion and Joule-Thomson coefficient. Now, in this lecture, that means in lecture 3, I will talk about Joule-Thomson effect for ideal and real gas and the temperature of inversion. What is the temperature of inversion and the relation of temperature of inversion with critical temperature and the boil temperature. Now, first of all, I write the Joule-Thomson coefficient that I already talked in my previous lecture, that means in lecture 12, lecture 2. Joule-Thomson coefficient mu equal to 1 by Cp times T del V del T at constant P minus V. This is the mathematical expression of Joule-Thomson coefficient. Now I obtain the Joule-Thomson effect for real gas. We already talked the interpretation of Joule-Thomson coefficient. When mu is positive, when mu is be positive, we get after expansion in porous plug experiment, Joule-Thomson porous plug experiment, the gas is cooled. And if mu is negative, then the gas after expansion in the porous plug experiment becomes hotter. So this indicates when mu is positive, it indicates the gas after expansion is cooled, and when mu indicates negative value, the value of mu, when the value of mu is negative, it indicates that the after expansion of Joule-Thomson porous plug experiment of the gas becomes hotter. So this indicates the positive value indicates becomes cooled and negative value indicates becomes hotter, becomes hot. So this negative value indicates hot and positive value indicates cooled. The gas is cooled after expansion. Now I want to obtain the Joule-Thomson effect for real gas. Now for real gas we know that for real gas we know that PV equal to RT for 1 gram mole of gas. Therefore V equal to RT by P. Therefore del V del T at constant P, del V del T at constant P equal to R by P, or from this relation R by P means V by T. And if I put this value here, if I put this value here, then I will get mu equal to 1 by Cp T into del V del T at constant P. That means this value equal to V by T minus V. That means it becomes 1 by Cp V minus V equal to 0. The mu, that is the Joule-Thomson coefficient mu for ideal gas, it becomes equal to 0. Thus, an ideal gas does not exhibit no temperature change in jet expansion. There will be no change of temperature in Joule-Thomson experiment or Joule-Thomson porous plug experiment. So this is the Joule-Thomson effect for ideal gas. Mu for ideal, it becomes equal to 0. Therefore we say that for ideal gas, thus an ideal gas does not exhibit does not exhibit temperature change in jet expansion. Temperature change in jet expansion. Thus, for an ideal gas does not exhibit temperature change in JT expansion. Okay, but the reverse, here we see that mu ideal gas equal to 0. That means when mu is 0, there is no change of temperature in the JT expansion. But reverse is not true. The ideal gas, mu for ideal gas is always 0. The mu for ideal gas always 0, but converse is not true. That means converse is not true. That means if mu equal to 0, the gas is ideal gas. It is not true. If mu equal to 0, the gas is ideal. This is not true. This is not true. That means this is not true. That means mu for ideal gas is always 0, but if mu equal to 0, we cannot say the gas is ideal, because if for real gas, suppose under a condition mu, I calculate mu for real gas and under a particular condition it becomes 0. That means it happen it will happen that mu for real gas equal to 0. Therefore we say that it happen when when the temperature of the initial temperature of the gas is equal to a certain temperature of the gas is equal to a certain temperature of a particular of this particular gas. Then there will be no change after expansion. There will be no change of temperature after JT expansion. So we cannot say mu equal to 0. That mu equal to 0 does not indicate that the gas is ideal. But for ideal gas mu always 0. I repeat again the point, mu always 0 for ideal gas, but mu equal to 0 does not mean the gas is ideal, because now when the initial temperature of the gas in JT porous plug experiment is equal to a certain temperature of the gas of this particular gas, then mu equal to 0. That means there is no change of temperature after expansion. That means in this particular case mu will be 0, and hence we cannot say mu equal to 0 indicate that the gas is ideal. Okay, now for real gas, for Joule-Thomson coefficient for real gas, Joule-Thomson coefficient for real gas, Joule-Thomson coefficient for real gas. Now from Van der Waals equation we have from Van der Waals equation we have P plus A by V square equal into V minus B equal to RT. Therefore P plus A by V square equal to RT V minus V. My aim is that since mu equal to 1 by Cp T times del V del T at constant P minus V, my aim is that I have to calculate these del V del T at constant P for real gas first, and then I put the value in this expression mu. Therefore I differentiating we get minus 2a by v square del v del t at constant p del v del t at constant p equal to minus RT by V minus B del V del T at constant P del V del T at constant P plus R V minus B into 1 or minus 2a by v square, sorry, this is not v square, it will becomes not v square, this is V, it will be become VQ, 2A by VQ, 2A by VQ plus RT by V minus B whole square. Here it will also becomes, this is square, okay, this is square into del V del T, del V del T at constant P equal to R by V minus B, R by V minus B. Now we get del V del T at constant P, del V del T at constant P. So we have, so U equal to 1 by Cp T del V del T, T del V del T, del V del T at constant P minus V, or 1 by Cp third bracket, we have to put the value del V del T at constant P, del V del T at constant P. Here del V del T at constant P, that means R by V minus V divided by this quantity. So it will become R by V minus B into, I just write here in this way, 1 minus 2, 1 by minus 2A by VQ plus RT by V minus B square minus V, right? I put this value del V del T at constant, del V del T at constant P, right? This becomes 1 by Cp, 1 by Cp. Here I write in this way, RT by V minus B into 1 by RT by V minus B square common, within second bracket 1 minus 2A V minus B whole square divided by VQ RT. This is, this way I write this equation, 1 minus 2A V minus B whole square divided by RT minus V third bracket close, or I, from here is RT V minus B and here is RT V minus B whole square. That means we get 1 by Cp third bracket in numerator V minus B divided by 1 minus 2A V minus B whole square divided by VQ RT second bracket close minus V third bracket close, okay, or it will becomes here mu equal to 1 by Cp V minus B into V minus B into within bracket 1 minus 2A V minus B square divided by VQ RT to the power minus 1 minus v. This is, now I expand in binomial form. We get mu equal to 1 by Cp v minus b, v minus b within second bracket 1 plus 2a by v cube into v minus b square divided by RT, divided by RT. I neglect the higher order terms, neglecting higher order terms, neglecting higher order terms, higher order terms, neglecting higher order terms. It becomes 1 by Cp, 1 by Cp here, v minus b into 1, and here is minus v, that means v cancel, minus b, and here we assume v almost equal to v minus b, therefore v minus b, therefore we write here this is 2a by RT, 2a by RT minus b. This is the expression of, this is the expression of Joule-Thomson coefficient for real gas. Now the value of mu depends on these value. It will be positive or negative, depends on 2a by RT and b. The value of the sign of mu, it will be positive or negative, it depends on 2a by RT and b. When 2a by RT greater than b, the value of mu is positive and the gas after expansion becomes cool, and 2a by RT less than b, then it will be negative, and after expansion the gas will be hotter, will be hot, and when 2a by RT equal to b, the value of mu becomes 0. That means there is no effect of temperature change in Joule-Thomson experiment when mu equal to 0. So I consider case 1. I consider case 1. Case 1. Now when 2a by R, when 2a by RT, 2a by RT greater than minus b greater than 0, that is T less than 2a by RB, 2a by RB, 2a by RB, then mu equal greater than 0. Thus for cooling effect, temperature of the gas before expansion, thus for cooling effect, for cooling effect, for cooling effect, thus for cooling effect, thus for cooling effect, the temperature of the gas before expansion, the temperature of the gas, temperature of the gas, of the gas before expansion, before expansion, before expansion should be smaller than, should be smaller, should be smaller than should be smaller than 2a by rb. 2a by rb should be smaller than 2a by rb for cooling effect. And when 2a by rt minus b less than 0, case 2, when case 2 when the when 2a by rt 2a by rt minus b less than 0, that is t greater than 2a by rb, t greater than 2a by rb, 2a by rb, sorry, 2a by rb, then mu is negative, mu is negative, less than 0, and this is, that is, the gas after expansion becomes hot instead of cooling, that is, it is heating effect, that is heating effect, that is heating effect. Now case 3, when the temperature of the gas T equal to 2a by rb. Now when temperature of the gas T equal to 2a by rb, 2a by rb, 2a by rb, mu equal to 0 and no change in temperature of the gas, that is no change of temperature, no change of temperature, no change of temperature of the gas, no change in of temperature of the gas in JT expansion, in JT expansion, JT expansion, there is no change in of temperature in JT expansion, right? Therefore the temperature 2a by rb, the temperature 2a by rb is called inversion temperature. Therefore the temperature T equal to 2a by rb is called inversion temperature, I for inversion. Ti equal to 2a by rb is called inversion temperature. When the temperature of the gas below this temperature Ti, it is cooled after jet expansion, and after expansion the gas is heated now when its temperature is greater than Ti. Now for this reason Ti is called inversion temperature. That means when the initial temperature of the gas less than Ti, that means less than inversion temperature, the gas becomes cool. When the initial temperature is greater than Ti, initial temperature is greater than Ti, then the gas becomes hot after the jet expansion. And when the temperature of the gas is equal to inversion temperature, that means the before expansion the initial temperature of the gas is equal to the inversion temperature, there is no change, of temperature of the gas. That means this is called inversion temperature, inversion temperature, inversion temperature, inversion temperature Ti equal to Ti equal to 2A by Rb, 2A by Rb. This is inversion temperature. Now when the temperature of the gas below this temperature, when the temperature of the gas, when the temperature of the gas, temperature of the gas, when the temperature of the gas below this temperature Ti, below this temperature Ti, the gas is cooled after jet expansion. The gas is cooled, the gas is cooled, the gas is cooled after JT expansion, JT expansion, after JT expansion, and the gas is heated when its temperature is greater than Ti, and the gas is heating, the gas is heating when the temperature, when the initial temperature, when the initial temperature of the gas, initial temperature of the gas, temperature of the gas is greater than Ti, greater than the temperature greater than Ti, and for this reason Ti is called inversion temperature. For this reason Ti is called inversion temperature, inversion temperature, inversion temperature. And if the initial temperature of the gas is equal to the inversion temperature, then there will be no change of temperature in JT expansion. Now the relations among inversion temperature, inversion temperature, boil temperature, BO, boil temperature, and critical temperature of the gas, boil temperature and critical temperature of gas, and critical temperature of gas, critical temperature of gas. The relation among inversion temperature, boil temperature, and critical temperature of gas. Here the inversion temperature Ti equal to 2A by Rb, 2A by Rb. This is inversion temperature, inversion temperature. This is inversion temperature. Boil temperature TB equal to A by RB. TB equal to A by RB. This is boil temperature. Boil temperature. Boil temperature means at this particular value of this temperature the real gas behaves like an ideal gas. Boil temperature. And next is critical temperature. Critical temperature TC equal to 8A by 27 RB. This is the critical temperature. Critical temperature means above which the gas cannot be liquefied. This is initial temperature indicates below the temperature of the gas. If the initial temperature of the gas below inversion temperature, the gas is cooled after jet expansion. This is the importance of inversion temperature. Boil temperature is the temperature at which a real gas behaves like an ideal gas, and critical temperature is the such temperature above which the gas cannot be liquefied by applying the pressure alone. So this is the importance of these three temperatures: inversion, boil and critical temperature. Now the relations among these three. From here we see that very simple relation Ti equal to T 2TB equal to 27 by 4 TC. This is the important relation of these three temperatures. This is the important relation of these three temperatures. Ti equal to 2TB equal to 27 by 4 TC. Okay.